Glee, you can go ahead and get a start on this if you want. Pull everywhere. So you, Helium, I went ahead and posted it. You can see it on. You can see it on Poll Everywhere. Yeah. I want to go ahead and get a head start on it. It's in Zoom, but it's also in Poll Everywhere. Where everyone else is at. Where's Josh, at least? Showing up. It's giving you all until 12:05. All right. So just in case you're just passively here, this quiz has been up for a little while, so make sure you're working on it. I've got no video, so I have no idea if you are working or not. That's just why I'm reminding you. All right, well, I've got, let's see, 2 in, 3. Ah, no, someone deleted. No? Cool, cool, cool. It's about 2 more minutes, which I'll get it in. All right, I've got 3 in. I'm just waiting on Josh. Let's give you 1 more minute, Josh, and I also came in a minute late. Otherwise, answers are looking good, y'all. Answers are looking good. All right, Josh, hopefully you're typing it in. At least get something typed in. So we make sure that we're moving on. There we go. I see your response now. Yep, it's something at least. So I'll take it. All right, so I'm going to lock answers here in 5, 3, 2, 1. Locking answers now. So most of y'all got it. And, you know, this is kind of the diagonalization homework that we were doing all last week. So though it's a little bit of a process, something that I try to give you at least relatively easier one to do. It's of course relative. But if we took the determinant to find that characteristic equation, we'd be taking the determinant of 1 minus lambda, 2, -1, 2, 4 minus lambda, and then -2, and then it was 3, not -1, 3, 6, -3 minus lambda. Okay. So we are taking the determinant of this matrix. This is what gives us our characteristic equation. You should have taken some of the time to go out and do this, but just for brevity's sake, I get to cheat. Well, not cheat. I get to shortcut this and just go straight to the characteristic polynomial, which would have been negative lambda squared times lambda minus 2. So this tells me that when I set this characteristic equation equal to 0, solve for the lambdas, I get 2 eigenvalues. I get an eigenvalue of 0 with multiplicity 2, and I get an eigenvalue of 2, which based off of most of your answers for your matrix P, you did get this. So then we fill in the lambda for the appropriate eigenvalue, row reduce, and figure out what our eigenvectors for these spaces look like. So I'd want to row reduce the matrix 1 to -1, 2, 4, -2, 3, 6, -3 for when lambda is being 0. So it doesn't look like I'm doing much, and that's because I'm letting lambda be 0 in that matrix above. If I row reduce this, this is just going to end up being the matrix 1 to -1, 0, 0, 0, 0, 0, 0, because I can see the second and third row are just multiples of the first. So that first equation then tells me x1 plus 2x2 minus x3 is equal to 0. And that x2 and x3 are free. So then anything in this vector space, any vector, eigenvector for this eigenvalue would be x1 would have to be x3 minus 2x2, x2, x3. And we split that up into the two variables that we see, a vector for x1 and a vector for x2. And if I do this for x2, I see that the vector is -2, 1, 0. And if I do this for x3, it's going to be 1, 0, 1. So these two vectors right here form the basis for my eigenspace, and those are going to be in two of the columns for my matrix P. Do a similar thing for lambda being 2. I'm going to consider then the matrix -1, 2, -1, 2, 2, -2, and then 3, 6, -5. And I take the time to row reduce this matrix, and it's going to end up being 1, 0, -1/3, 1, 0, -2/3, 0, 0, 0. Then that tells me we get the equation x1 minus 1/3 x3 is equal to 0, x2 minus 2/3 x3 is equal to 0, and x3 is free. So then all of my vectors for all of my eigenvectors for this eigenvalue are going to be of the form some constant times 1/3, 2/3, and then 1. And that's going to make up another column for my matrix P. So the matrix P, the order of the columns only matter depending on what you set your diagonal matrix to be. I never asked you to set your diagonal matrix because I only wanted you to have to enter in one matrix into poll everywhere. So one good choice for P could be just kind of the way we have it written here. -2, 1, 0, 1, 0, 1, 1/3, 2/3, 1. Okay. So for a correct answer for this, it just needed to be any organization of the columns. All right, you could have done 1/3, that 1/3, 2/3, 1, that could have been your first column for P, and I needed other two vectors. But these are how we get the vectors, and this is how we get that matrix P. This is what you should have been doing. So looks like I think everyone who at least had enough time to do it got in a good answer. So I think we're good there. But any questions? If not, give me a thumbs up, please. Cool. I got 3 people listening, at least. Or 2 people not asking questions. All right. So, cool. Thank you, Nabari. All right. So today we're going to move on, and we're going to take a step in what seems like a different direction. But this is, again, building the theory so that if I'm trying to solve this system, Ax equals b, if I can diagonalize that matrix A, then find a quick way to solve it. But one of the issues that we said is, even if we diagonalize it, I'm finding this matrix P, and then I need to find that P inverse. I guess I should do other way. So what we're looking for right now is maybe a way that, since I'm building this matrix P, can I build it in a nice way so that the inverse is either very easy to calculate or there's not really any trouble to do that at all. This is where orthogonal will be orthogonal matrices, orthogonal vectors, and orthogonal spaces comes into play. Because what we're going to do is we're going to be able to show, we're going to define a particular vector where its inverse is just the transpose. Okay. We're going to look to build that type of matrix. So today we got to start with the basics. We got to start with our operations, and we're talking about dot product. Okay, if I let two vectors be in Rn, so x and y just be vectors in Rn. Then we define the dot product of these two vectors just to be the transpose of the first vector times second vector. Which means then that if we have n entries, this is all the x entries, all n of them, multiplied by the vector y, which if I then do that matrix multiplication, it would follow first row by first column. Well, it's just a single row and a single column, and I followed that matrix multiplication that we set up. I see that I'm just multiplying each pair together and then adding them all up. So this is the dot product. This is how it is defined for a Euclidean space. And we use that dot product to measure things because it actually tells us whether or not vectors are orthogonal. It gives us some relationship between vectors. So we have that definition for orthogonal vectors. Whoops.
I have a question.
What's up?
So you find the dot product of two matrices, and that tells you if they are orthogonal?
Well, we're about to define it. We're about to define what orthogonal means. But yes, you're going to have to do the dot product of two vectors specifically. We're talking about vectors in our Euclidean space Rn. So two vectors in Rn in our Euclidean space are orthogonal if their dot product is equal to 0. Okay. We say two vectors are orthogonal if their dot product is equal to 0. Okay. So we gotta just kind of remember, you see it in the videos, he talks about in the videos, vectors are talking about direction. Right? I travel so many units this direction, I travel so many units in that direction, etc. And we can always view points in 2 dimensions. So in R2, this just means we have 2 dimensions, and all of our vectors are going to be considered an x value and a y value based on my x-axis and y-axis and wherever they're at. So I could have a point right here, which would be at, just say 1, 1. I create a vector. So that vector then would be the vector 1, 1. And what orthogonal is describing is another vector that is perpendicular to it. So I can take another vector and I draw it, and if I measure the angle between the two vectors, then I would have a 90-degree angle. So an easy way to create a 90-degree angle for this example is then say, okay, well, go in the direction -1, 1. So make that my second point. I can create another vector going from the origin to that particular point. And for this one, the vector will be, well, the x value is -1, the y value is +1. And this naturally creates a 90-degree angle between those two rays, between those two vectors. And I see that if I take the dot product of these two vectors, the 1, 1 dot with -1, 1, which we define just to be, take the transpose of the first, multiply it by the second, do my matrix multiplication there. I do row times column, which means this is going to be 1 times -1 plus 1 times 1, or -1 plus 1 is equal to 0. So in 2 dimensions, we called orthogonal vectors perpendicular. We call those lines perpendicular. But we can generalize that concept of perpendicular to more dimensions. And I could do this in 3 dimensions. I could do this in 4 dimensions, 5 dimensions, etc. And this is how we test for it. We test to see, okay, can I show 2 vectors are orthogonal by taking the dot product, and if that dot product is 0. If it's not 0, then I can't draw a 90-degree angle in some way between these 2 vectors. Okay? So I'm going to get y'all to do a practice example here in a second, but questions? If not, give me a thumbs up. Cool.
I have a question.
Yeah, go for it, Josh.
So what we're doing here is we just adding vectors, I guess, right?
Not adding, we're doing the dot products. You multiply the dot product because of how we do the matrix multiplication, how we define it with matrix multiplication. You just take corresponding elements, multiply them together, then add them all up. If that's kind of a way you want to sum up the dot product, which is what was written here.
Okay.
Cool. Any other questions? All right. So do this example. It's not going to be in poll everywhere. I'm going to do that whole 3, 2, 1, go thing. I want you to just type your answer into Zoom meeting chat. Don't hit enter until I say to. So just have it kind of ready for me. So are the 2 vectors 2, -3, 1 and 1, 1, 1 orthogonal? Are these 2 vectors 2, -3, 1 and 1, 1, 1, are they orthogonal? You type your answer yes or no into chat, but don't hit enter. Do not hit enter. Wait for me to tell you to enter. Just that way we can kind of get everyone's answer at once. I'm going to give y'all just 1 more minute to get it in, to get ready to be typed, because I just want a yes or no. Do the calculation and tell me. But don't hit enter. I keep saying that, because I know we haven't done the 3, 2, 1, go thing in a while. All right, so go ahead and type in your answer. And I'm going to want you to hit enter here in 5.
Wait! Oh
What?
my, too fast.
It's not too fast. You got to do 3 multiplications and add them together. I'll give you all another minute though. At least thank you for speaking up. I should say that. Thank you for speaking up.
Thanks for the time.
How about this? Give me a thumbs up if you're ready to go. Because I can't see anyone working.
I cannot give a thumbs up. I'm at work, so what you were saying a few minutes before, I didn't get to hear it. Oh my.
Okay, well, all we're doing is trying to figure out if these are orthogonal, and they're orthogonal if their dot product's equal to 0. So all I need to do
Yes,
is
I did see up to here.
Yep, so that's all we're doing, is we're just calculating dot product of these two. If it's 0,
Okay.
they're orthogonal. If it's not 0, they're not orthogonal. All right, so I think most everyone got thumbs up for that are able to give me a thumbs up. Oops, so the bar unmuting for a little bit. All right, so hit enter in 3, 2, 1, go. All right, yep, they are orthogonal. So if I take the dot product of these two matrices, 2, -3, ooh, that's bad, -3, -3, 1, and 1, 1, 1. This means I'm just taking the transpose of that first one, 2, -3, 1, multiplying it by the vector 1, 1, 1. This gives me my row and column to match up with for my matrix multiplication. But it just says take each corresponding element, multiply them together, then add them all up. So this will be a 2 times a 1 plus a -3 times a 1 plus a 1 times a 1. And then I just add these up. 2 times 1 is 2. I'm subtracting a 3. I'm adding a 1. 2 minus 3 plus 1 is 0. So these vectors are orthogonal. Since there's 3 dimensions, I would be thinking about in 3-dimensional space. But in 3-dimensional space, I'd be able to draw a 90-degree angle between these two vectors. Okay. So just quick calculation. We're going to do another one, but any questions?
I don't have any questions, but I do understand now.
Cool. Thank you for letting me know. All right. So this one I just want to give you all because there is a notation for vectors, especially for 3-dimensional vectors, because it comes from calculus. Instead of writing them like, let's say 1, 2, 3, that we're kind of used to, they can be written as more of almost a transpose of that. So this is another way you'll see vectors being written, but they're just representing the same thing. This is a vector where the first element's 1, second element is 2, and third element is 3. Okay, so let me draw an arrow back and forth between those at the top. The question that I want to ask you is, are the vectors 3, 5, -1, and 1, -1, -2, are they orthogonal? It's the same type of question. I want you to answer the same way. Just type it in. Don't hit enter until I say 3, 2, 1, go. I just wanted you to see that there is a slightly different notation that is commonly used, and I want to make sure that you are exposed to it. Okay, but the process, the idea does not change. Find the dot product. If it's equal to 0, they're orthogonal. If it's not equal to 0, they are not orthogonal. Give me a thumbs up when you are done.
Professor, I have a question.
Yeah, what's up?
Not regarding the problem we're doing right now, but the overall properties of the work.
Okay. Do you mind asking after we're done with this example? Or waiting to ask?
Yeah, that's fine.
Cool. Yeah. I'm guessing that means you're done with this one?
I would think so. Yeah, I am.
Cool. So I'm going to ask here in just like 30 seconds-ish for everyone to hit enter. 30-ish seconds. So for me, that'll be 131. All right, make sure you have your answer typed in. I'm going to ask you to hit enter here in 3, 2, 1. Hit enter. Go ahead. Go, go, go. Yeah. Got people going at the same time this time. All right, so the answer is actually yes. Sorry, Josh, but it is okay. We're going to go through it. All right, so I take the dot product of these 3 vectors. I can leave it written with this, little less than greater than signs on either side of it, or I can just convert it to the notation that we're more familiar with using the square brackets. So this is a vector 3, 5, negative 1, taking the dot product of it with 1, negative 1, negative 2. Yeah, that's all good, Josh. Don't make mistakes. That's what we're learning. Don't care that you made one. Do the dot product, and it's just multiply the corresponding entries and add them all together. So this is going to be a 3 times a 1 plus a 5 times a negative 1 plus negative 1 times a negative 2, which gives me a 3 minus 5, not plus, minus 5 plus 2, which is equal to 0. So again, the vectors that we were given are orthogonal. Okay. So again, if I drew these in 3-dimensional space, so they have an x direction, a y direction, and a z direction, I'd be able to draw a 90-degree angle between these two. All right, Elliot, what's your question? Thank you for waiting.
My question is, so I was reading, I was watching the videos, and I think one of the properties said that that product is commutative. You can, so I could do 1, negative 1, negative 2 transpose times 3, 5, negative 1, and get the same answer.
Absolutely. So let's do it. 1, negative 2. What was it 3? Oh crap! I already forgot. 3, 5, negative 1. Right? Those are the correct. Yeah. So again, I would just say, okay, then this is, like you said, 1, -1, -2. So the transpose of that first one times 3, 5, -1. This will still be 1 times 3 plus -1 times 5. I have to drop down a little bit because I won't have room there, but plus -2 times -1, which still gives me 3 minus 5 plus 2 is equal to 0. Yeah, so dot product is a nice operation. It's not only commutative. So what Elliot was talking about, if you don't remember off the top of your head, commutative means it doesn't matter which order you operate these two vectors, whether you do x dot y or y dot x. Yeah, so either way, you're going to get to the same answer. Any other questions? All right, so let's talk about some more properties, definitions, things we can do with these vectors in Rn. So one of these is called the vector norm. Okay? It measures the distance of the vector, how far you have to travel from your origin to the tip of that vector. And we define it in the following way. So just take some vector in Rn. So it has n entries. It could be 2, 3, 5, 100, whatever. Oh, what's up?
Vector norm is the distance between the perpendicular points.
Between the origin and the tip. It's how along the line. I'll show you an example in a second because you've already seen it before plenty of times. It's called Pythagorean theorem. But just take any vector Rn, so it doesn't have to be 2 dimensions, which is where Pythagorean theorem shows up. It can be in n directions, 5, 500. You don't care. The norm of x, my vector x. So you're going to see these two. I don't know why. There we go. Finally showing up. These two lines, almost like absolute value. So you know absolute value is a single line on either side. Norms is going to be 2 lines on either side. We define it by taking x and doing the dot product with itself.
So that x with the double lines, does that have to do anything with absolute value?
In the first dimension, it would be the absolute value. You're doing it in single dimension. This is a generalizing absolute value. You can see it here in a second once we actually write down the definition.
So it would just be that number by times itself.
And then you take the square root of it. Because when I take the dot product with anything by itself, what ends up happening, oops, I forgot to write the 1/2 because I need to take the square root of it. What ends up happening is I'm taking the square root of every element of that vector and squaring it, adding together. So how we define this norm, our generalization of absolute value, is just that we take the dot product of the vector with itself, take the square root of it. If we go ahead and evaluate that dot product, what ends up happening is you take every element, you square them, add them together, and then you take the square root overall. All right, so your mic unmuted. What's up, Ellen?
Oh, no.
Gotcha. All good. Cool. So like I was saying before, in R1, this just is going to be the absolute value. Because if I'm in R1, that means my vector is something like 2. Right? It's just a single number, which we never really write as a vector. We would just write as 2. So the norm of this vector would just be taking the transpose of it, which is just 2, taking the dot product of itself, or with itself, and then taking the square root of it, which becomes 2 times 2, or 4, and I take the square root of 4. Whoops. And it just acts like the absolute value. Out of change this up to -2, it'll become the same thing because a -2 times a -2 gives me a +4. I take the square root of +4, it is a 2. Now in 2 dimensions, really you're talking about kind of the length of a hypotenuse, the hypotenuse of a triangle, because any vector in R2 is just pointing towards some point in space, coming from the origin, pointing to some point. And that point is going to have an x and a y value, which means that it's got both a height and a length. And I can see from there, if I draw this on that coordinate, I get a nice triangle. Where this is my vector that I care about, I'm caring about the distance of that vector, and I can get it because this is a nice bright triangle, x and y, and my hypotenuse will end up being the square root of x squared plus y squared. A squared plus b squared is equal to c squared. And so in R2, I even see that show up.
Wait, I have a question.
What's up?
So you started with the -2, the norm of -2, which is the same as -2 times itself. And that gave you your hypotenuse?
That's in 1 dimension. I went on to 2 dimensions for the example. Next example.
Oh.
Saying in 2 dimensions, the norm is just finding the hypotenuse of a triangle. The same equation. Okay? But really, when you're talking about finding the hypotenuse of a triangle, we can view it as finding the distance of this vector. So norm is a way to get the distance, how long this vector actually is in its space. And it's a generalization from what we naturally know in R1 and R2. But now we can do it for many more dimensions. So, got a couple definitions I got to get through because I want to get them done before the end of class today. But, whoops, I don't want to write in green. So another definition, another term that we're going to use, and that's needed for when we're trying to build up again that nice way to diagonalize matrices. Definition is that we have something called a unit vector. Unit vector is a vector with a nice special property. That property is that its norm is a good old 1. The norm is a good old 1. Okay. Unit vectors are nice because we're going to see that that norm is going to be a value that we're going to want to start calculating in various processes. So if I can identify a unit vector, that means its norm is 1. That means I'm just using the value 1. Adding, subtracting, multiplying, dividing, I'm just doing it with a 1. And so that's what a unit vector is. And essentially, we care about unit vectors because any vector is pointing in a particular direction, but I can always scale it down to a unit vector. I can always turn it into a vector pointing in the same general direction, just with much less length, or a length of 1. So, for example, I can have a vector pointing in whatever this direction xy is, but But I can make smaller and smaller vectors that don't take as much length or don't have as much length pointing in that same direction. And so this would be my vector v, or that blue line could be a normal vector, and that red line would be my unit vector. Pointing in the same direction, but it's got a length of 1. Well, again, this is because we can scale this back. It's nice and easy to scale it.
So the red line is the one that has a norm of 1, the vector with a norm of 1.
Sure. I think I said that. So yeah. But the idea is you can always scale back vectors, right? Any vector that's out there, I'm going to be able to scale back, still preserve the direction that I'm pointing, but keep its length to a nice, good old 1. And how you do that is relatively simple. I just need to have a length of 1, so I take that vector and divide it or multiply it by 1 over its length. So to get a unit vector, from an existing vector, all you need to do is figure out what the norm of that vector is, divide each entry by it, or multiply it by 1 over that norm. So that norm is going to give me a number. I take 1 over that norm and multiply and do that scalar multiplication for every entry in that vector x, and that will give me a unit vector. So I calculate the norm, take it as 1 over that norm, multiply it by my vector, that gets me a unit vector in that same direction. Vector pointing in the same way, just with much less length, and we see it here, I'm just scaling, right? I'm taking whatever the length of the vector was, and I'm just reducing it, all of the values by that length to get to that magic number 1. So let's do an example.
So Professor, norm is the same as length?
Yes, norm and length are the same thing.
So to get the
Norm
unit vector,
describes the length.
so to get the unit vector, you find the norm and just put it over 1 times the
Multiply
given
it
vector.
by that vector. -1, -1, 4. Find a unit vector, which we'll just call U. It is in the same direction. So this is where we just need to take that unit vector and just set it equal to 1 over whatever the norm of this x vector is. Take that and multiply all of the entries of my x vector by 1 over that norm. So we got 2 steps: calculate the norm and then figure out what this new matrix U is going to be. You have a question, Alien?
No.
Oh, okay. Sorry. I thought I heard you. My bad. I was afraid I was talking over you again. I was like, ah. All right. So I want you to find U here. We're actually almost out of time. Wow. So I'm going to just hopefully do it along with me. Maybe you're just already working on your own. The first thing I need to do is find the norm of this vector x, which means that it's going to be, ooh, someone's sneezing, x transpose times x, taking the 1/2, which we said, just take all the entries. This ends up turning into taking every one of the entries, squaring them, adding them together, and then taking the square root of that value. So I take the first entry and I square it. I add it to the second entry and I square it. Add it to the third entry squared. Add it to the fourth entry squared, which is going to be the square root of 16 plus 1 plus 1 plus 16. or the square root of 34. So that is the length of this vector in 4 dimensions. It is the square root of 34. But my goal is to find the unit vector. So then I take 1 over the square root of 34 and multiply it by every element. So this is going to be 1 over the square root of 34 times that matrix 4, negative 1, negative 1, 4. Or if I just went ahead and did that scalar multiplication, this would be 4 over the square root of 34, negative 1 over the square root of 34, negative 1 over the square root of 34, and 4 over the square root of 34. This vector, this new vector, is still pointing in the same direction. All I've done is reduce its length so that the new length of this vector will be 1. If you went ahead and took the time to do the norm of u, by construction, you would see that it is going to be 1. You can do the calculation on your own, but it will come out to be 1. That's what we mean by unit vector. It's just a vector of length 1. We're able to get that by just scaling appropriately, by dividing by the distance. Okay, so questions?
Yeah, I have a question.
Yeah, go for it, Josh.
So you said you will be 1 for this matrix?
So
Not matrix.
we created the vector u so that it would have a length of 1. So the norm of this vector u would be 1.
Oh, okay.
Cool. Any other questions? All right, well, it is 12:50. I'm going to have to continue this on Friday. This kind of gets you through at least most of the homework, so you can at least go ahead and start attempting that. We'll talk about what it means to be orthogonal to a set on Friday, and then we'll also just do an example of that and also something called the Gram-Schmidt orthogonalization process. Once we have all of that theory built up, I'll show you why it is useful for diagonalization. So make sure you go ahead and starting that homework. I know a lot of you are have that bad habit of waiting until the day it's due when you don't need to. You can go ahead and start doing it now. Don't stress yourselves out, especially for those of y'all in 241 where you have homework in that class due on the same day. Okay? Don't stress yourselves out. Be proactive. Start working on it. That's it. Any questions for me? If not, you're good to go.
No questions.
Cool. Thank you for speaking up, so I knew.
All right, Professor, you have a good day.
Yeah, you do the same. All right, any questions from y'all?
Yeah, I think I have one more question.
Yeah, go for
Okay, this one was about what do you call it? The daily quiz.
it. Mm-hmm.
But the multiplicity of 0.
Yeah.
Yeah, I know how you get the 2.
So there was the work there.
Okay, yeah, I know you get the negative 210, but I'm not sure how you get the other 110. Not too sure on that one.
So it comes from what we were doing down here. So we found out what the vectors, my eigenvectors for lambda being 0, what they have to look like. So x2 and x3, we have two free variables. They can be any value. But what goes in that first entry, if I solve it for the first entry, it'd be x1 is equal to negative 2x2 plus x3. So negative 2 of whatever the second entry is plus the third entry. Or I can rewrite this as x3 minus 2x2. So as long as my vector looks like that, then I can create an eigenvector for the eigenvalue lambda being 0. But then we say, okay, look at this eigenvector, this general eigenvector. We said, okay, there's two variables that it depends on. So I can rewrite this as a linear combination of those two variables, which the first step would have been saying, hey, take this, set it equal to, well, separate my x2s and my x3s. So I'd have a negative 2x2, an x2, and a 0. And I'd be adding this to x3, 0, x3. Coming from splitting up that vector right there. Okay. But then that's when we said, okay, I can factor out an x1 and x2, or sorry, an x1, x2 and an x3 from both of those. And that's what we have. Let me recircle it. That's what we have right here. So then any eigenvector, as long as I choose x2 and x3, will be just a linear combination of negative 2, 1, 0 and the vector 1, 0, 1. So that creates the span, the basis for my eigenspace. And that gives me two linearly independent eigenvectors for the same eigenvalue that I can use in my matrix P. Because one of the requirements was we needed eigenvectors that are linearly independent.
Okay, yeah, I got it. I saw what I didn't do. Okay.
Awesome. Awesome. Just want to hear, I get it now. That's what I want to hear. All right, Khalid, you got any questions or are you just hanging around?
Just listening.
Josh, you got any more questions?
No, that was all.
All right, well, I will see both of y'all on Friday unless you set up a meeting to meet with me during office hours. So, see y'all
Great.
Friday.